Hi guys, welcome to the video for tutorial 9 industrial chemistry. Okay, so this topic is all about designing chemical reactions in the industrial setup. So first we need to look at the 12 green principles of chemistry. So these are the 12 green principles, and of course you are not supposed to memorize all of them. So when you go through that one by one, you will realize that they are actually more or less the same. They're trying to reduce any toxicity or any hazardous impact to the environments. All right, let's go through it quick. So the first one is prevent waste. So when we design a chemical reactions, we try to reduce the productions of byproducts, right? We try to reduce the waste rather than cleaning it up later. All right, second one, maximize atom economy. Like I mentioned before, we try to maximize the amount of atoms in the reactant and convert it 100% into the product, into the desired product, not the byproduct. All right. So number three, less hazardous chemical synthesis. See that? So they're trying to reduce the hazardous effect to the environment or to the human being. Number four, safer chemicals and products. So we're trying to use a safer chemicals before we talk about the toxicity of the product form. So it is good that to produce a product with zero toxicity or with low toxicity, and same goes to the reactant that we use or the raw materials that we use. Now, what do we call that when we talk about raw materials in a chemical reactions or in an industrial process? We call that as a feedstock. Okay, the feedstock, the raw materials that we use before we actually get our products in stages. All right, safer chemicals and product. Number five, safer solvent and reaction conditions. Safer solvent, again, is the same thing. They're trying to reflect that the solvent that we use, we try to choose the one with less toxic. Okay, and the reaction conditions, we try not to use high temperature or high pressure because that will actually use up a lot of energy. We try to save energy. It's good that a chemical reactions that can occur at ambient temperature, like room conditions. All right. So number six, increase energy efficiency. Again, we try to save energy during a chemical reactions without using high temperature. Use renewable feedstock. Now that's the thing. So the raw materials that we use is good that it is renewable. Fossil fuel is definitely not part of it, right? But most of the chemical reactions that we are having it today, they're actually using fossil fuel, right? So number eight, avoid chemical derivative, as in when we have a chemical reactions, we try not to change a functional group. So what does that mean? For example, let me show you in the examples. If I have a reactions of COOH, right? This is an R group. I'm sure you guys know what is R group now. And then add up with an alcohol. See that? So obviously this is an esterification reactions. You will get an ester, COOCH3. Now, these reactions need to heat under reflux, which means, what does that mean by heat under reflux? You need to heat above the boiling points of both reactants. And then under conditions where it keep boiling for a longer period of time. So you need to maintain the high temperature, and then you need to add a concentrated H2SO4. This is highly corrosive because when it is concentrated and it's a strong acid, right? So we try not to use the high temperature and as well as the corrosive solution. Like here it says safer solvent. We try not to use a corrosive solvent, like in this case sulfuric acid, and we try to increase the energy efficiency for these esterification reactions. And what we can do, we actually can change these things into some other more reactive compounds. How to change it to become more reactive, where the reaction can actually happen at room temperature without heat under reflux. How do we do that? It's very simple. Look, if we're changing it, we just need to use this RC double bond O OH, right? You just need to add with COCl2 oxyl chloride, and what will happen is the RCOO will change it into RCOCl, carbon dioxide and water. So this is the main thing. So initially I have carboxylic acid, which is COOH, and then after reactions with this, I'm changing it into COCl. Now listen carefully, Cl here is actually more electronegative than the OH in this case, because the O here is attached to H as well as to the carbons, right? So the electronegativity is actually pulling electrons from both oxygen and hydrogen. But here, if you look at the Cl, they only pull electrons from the carbon here. So what will happen to the bond length here, the distance between C and Cl? It will be further away, because it keeps pulling electron towards itself, and then it weakens the bond. When it weakens the bond energy between CCl is actually weaker than between COH. If that's the case, it is easier for us to remove the Cl rather than the OH in an esterification reactions, right? Because we tend to form water from these esterifications to form an ester. So if the Cl is easier to remove, then the whole reaction will be much simpler and much easier. So that's the case. So once we have changed it into Cl instead of OH, COCl, we call it as a acyl chloride or acid chlorides. Okay, no longer carboxylic acid, but this is actually a derivative of carboxylic acid, a derivative which changes to the functional group, but it's still under the same family. So in this case, what happened between the reactions of OH, the H will remove, the H will remove. Instead of getting water, you're getting HCl. But once we have changed this, we don't need concentrated sulfuric acid, we don't need heat under reflux. The reaction can actually happen at room temperature, and then the rate of reaction is vigorous. All right, it's much faster than you're using heat reflux and concentrated sulfuric acid with COH. So that is an advantage of using a derivative, right? So we fulfill these two, guys. We fulfill number 5 and number 6. See that? We are trying to use a safer solvent. We are trying to increase the energy efficiency. But at the same time, we're actually violating number 8. See that? Avoid using chemical derivative. And why is it bad to use chemical derivative here? Can you see that? The byproduct produced is HCl, which is corrosive. As compared to before that, it was supposed to be water. But now, the rate of reaction increase, everything looks good. The only thing bad is, at the end, I'm producing a hazardous waste, a hazardous byproduct. So you see that? Among the 12 principles, we are trying to take a balance point between all. We can't actually fulfill every single principles in this among these 12. No, that's impossible. I mean, of course, that would be ideal if you can do that. All right. So we try to take a balance here. Now, since we can actually fulfill these two, and then we violating one. All right. And then anything else? No, the rest I don't think so. We have ways. You see that? So we have to take a balance between that. You have to analyze. The company itself have to do an audit to this process. How do we balance it? Fulfill more of the 12 principles, all right, so that we can minimize environmental impact. All right, so this is how it looks like for changing the derivative. Now, number 9, use of catalyst. Now, this one everybody know. With the use of catalyst, we actually reduce the activation energy, and then we don't need to provide that much of heat. So this thing is also complementing increased energy efficiency. See that? All right. So number 10 is design chemicals and product to degrade after use. Now this is very important, because after we produce a product and it serves its purpose, for example, in the Haber process, we are producing ammonia gas, and ammonia gas convert into fertilizer, and this fertilizer serves its purpose in the plantations, right? But after that, what happened? What happened to this fertilizer? Would it cause another environmental impact, environmental problems to the environment? Yes, because excessive use of fertilizer, it causes algae bloom in any water sources, right? It causes algae bloom in any water sources. So if that's the case, what happened is algae bloom were actually bad in terms of preventing UV lights, and also the nutrients or the dissolved oxygens in the water. So that will actually affect the living organisms in the water, in the oceans. All right. So that is actually bad things. So we have to actually take this into consideration as well. So the product that we produce after it served its purpose is supposed to degrade by itself without causing any environmental problems. All right. Next, analyze real time to prevent pollution. This is also important because, like our water pollution cases that happened recently, if we manage to identify it earlier, we don't have to actually wait until it is too late. For example, when we consume the water in our house, all right, from the indoor water, right? So they provide water in, and then until we actually detect that, oh, some weird odor from the, or weird taste from the water that we are consuming, and then only we inform the authorities, and then they realize that the pollution is too late, and they have to stop the supply. So they have to cut it off. When they cut it off, we suffer, and then they need time to clean it up before they can resupply the water sources to our house. So that is another reason why we have to analyze anything in real time. For example, when the water sources with certain chemicals more than the minimum, more than it should be, the detector will inform the authority that, oh, now water is bad, it's polluted, so it's time to stop it. And that's how we cure it. Not until it's already distributed everywhere and then the consumer actually complain, then only they take actions. So this is also an important factor that we should consider. And number 12, which is the last one, minimize potential for accident. So in the industrial process, there's so many things that we have to consider. One of it is actually like temperature that we use. Now, what if the reactions like Haber process, contact process, we are using high temperature, 500, 600, or 1000 degrees Celsius. And these will actually increase the probability of having an accident. So what if energy leakage? What if gas leakage? And under high temperature with the gas or with the powder's catalyst, that will cause an explosion. So we try to minimize all these things in order to avoid accident. So this is another factors that we should consider. And it seems a lot with the 12 principles that we should consider. All right. But yeah, like I mentioned, we need a balance point among all this. And we can't achieve an ideal condition. So whatever we planning, whatever we're designing, those who are going for chemical engineering, you have the design plan, you have the design reactions, right? These are the things is in our first considerations. We have to go through the 12 principles. Out of the 12, maybe we can actually violating one or two. That is good enough. So out of 10, out of 12, we actually fulfill 10. And then another 2, sorry, because it's not ideal, right? So that is good. Or maybe 50%, that's minimum requirement, I guess. So yeah, that's important for you to consider. That's the 12 principles of Green Chem. All right. So let's move on to the tutorial questions. We have talked a lot here. Okay, for question 1, construct a flow chart of the synthesis of ammonia from methane and air. Now, I don't expect you guys to come up with a proper plan or proper flow chart because we don't learn it yet in a way, or it's too early for you to actually figure out how a flow chart works for the synthesis of ammonia from methane and air. So that I'm going to explain it briefly on how does it work. Now, this is an example. If you Google search it, there's so many, tons of these images will come out in your Google search result. Now, let me explain briefly on this. To form ammonia, we know that we are adding hydrogen gas plus nitrogen gas to form ammonia. This is what we learned, right? Haber process. 1:3 ratio between nitrogen and hydrogens. And this is an exothermic reaction. And this is what we learned. And what is the conditions used, guys? Temperature is about 450 degrees Celsius to 550 degrees Celsius. All right. And then catalyst used is iron, solid, iron powder, finely divided powder. And then we learn about pressure as well. What is the pressure for this case? 100 to 200 atmosphere. Right? So these are the specific conditions for Haber process. This is what we learn, as simple as that. But the thing is, in actual conditions, in the industry, do we have hydrogen gas and nitrogen gas as our feedstock? No, we don't have available hydrogen gas. Nitrogen, maybe because we have 70% in the atmosphere, we can have nitrogen gas anywhere. We just need to compress it. We just need to do gas distillations. We can get a nitrogen gas. But what about hydrogen gas? Hydrogen gas is a flammable gas. It's an explosive gas. How do we get that? We need to depend on other chemical reactions before we get our raw materials, hydrogen and nitrogen, and then only we can get an ammonia. So how do we get that? So for the synthesis ammonia, we need methane gas and air. These two are our feedstock or our first step in producing ammonia. All right? Specifically in producing hydrogen for the synthesis of ammonia. So methane gas is a natural gas from the distillations of fractional distillations of a fossil fuel, right? So first we have natural gas. All right? Go through cleaning. This process we call desulfurizations. Okay, what is that desulfurization? We try to remove sulfur. Now, sulfur is a naturally occurring element in fossil fuel. So we have to remove sulfur to avoid poisoning of the catalyst used in this whole process, so the synthesis of ammonia, or to remove impurities because we are trying to avoid the formations of byproduct. We maximize the desired product according to the green principles of green chem, right? So now we're cleaning it up. We use zinc oxide, and at the end it gets zinc sulfate. See that? They're removing sulfur from it. We call it as desulfurization. After cleaning it up, we go into reforming. Now, reforming is the process of changing natural gas into carbon monoxide, carbon dioxide. Basically combustion, but in a controlled conditions. So we are burning it in limited amount of oxygen so that we get both carbon monoxide and carbon dioxide gas. Still remember complete combustions. If it is complete, then we will get only carbon dioxide gas, right? So in this case, we are trying to control it so it will get carbon monoxide and carbon dioxide together. Okay, that's the reforming process. After that, we will add in steam, all right? So the steam together with carbon monoxide from the structure, from the reactions, these two, they will react. They're so-called the syngas. They will react to form a shift gas. And this reaction, we call that as water gas shift reactions. So we are converting the carbon monoxide and water into hydrogen gas and carbon dioxide. All right, that's the water gas shift reactions. And after that, we carbon capture it, or we call it as methanations. Methanation means we're trying to capture whatever unburned carbons in the process, whatever unburned carbon monoxide or whatever things. All right, so we try to capture it and convert it into steam or into recyclable procedures and back to reforming. So whatever excess of carbon monoxide that not in use or carbon dioxide, we convert it back to this reforming process and to recycle it so that it will reduce the waste. See, one of them, the green chem, reduce waste. And then once we remove all the excess of carbon, we are doing a purifications on the hydrogen gas produced, right? This one. So once we get a hydrogen gas, then it will go into this reactor, so-called the reactor, and then it reacts with the nitrogen gas that we distillated, and then both react to form ammonia gas. So this is the whole process of synthesizing ammonia from methane and air. All right, so that's the first question. Basically, you don't have to explain all this. You just need to learn this, and you basically just need to show the flow chart. So that's why I might as well just explain the whole thing. Now, the next slide, this is the reaction mechanism. How does carbon monoxide and water mix together? How these things actually mix together? A syngas. This is called a syngas. Sorry. A syngas. And then after that, end up you are getting your hydrogen gas and your carbon dioxide gas. So how does it work? So follow the green arrow. Follow the green arrow. This is the proper way. You absorb at this catalyst and then all the way until you get that. I guess I will explain that in your tutorial session for this mechanism in detail. All right. You can read it up first. You see all this activation energy is given, and there's alternative. The black arrow is an alternative route. See, 0.61 activation energy, 1.76. This is not preferable. and 0.23, maybe this. And how is it reduced in activation energy? Maybe they are using different catalysts. This is actually a catalyst, guys. This is a metal catalyst. All right, so this is the whole process until you get a hydrogen gas, and this is how it works. And then if you still remember, guys, what do we call this as? Homogeneous or heterogeneous catalyst? All right, give me an answer during the tutorial sessions. All right, that's next. Now, number 2. A farmer is looking at add a nitrogenous fertilizer to one of his fields. So he has a choice of purchasing 50 kgs of ammonium nitrate or a urea. So 2 options here. One is ammonium nitrate, NH4NO3. Another one is CONH2. All right. So the first questions: which fertilizer will give the most nitrogen to the soil per 50 kg bags? See that, per 50 kgs bag. So which one giving you the most nitrogen per 50 kg? So how we do that? In a simpler way to do that, I will just use this. Now, how many nitrogen do we have here? Let me change the color. We have 1 nitrogen, 2 nitrogen. So total is 14 times 2. That's the molar mass. And then divided by the molar mass of the whole thing, which is, wait, let me calculate. 28 plus 4 plus 48. So it's 80. And then you times 100. You will get the percentage of nitrogen from this compound itself before we talk about a 50 kg. So 28 over 4 over 80 times 100, you're actually getting 35%. So you have 35% of nitrogen content from this ammonium nitrate. And what about this urea? Do the same thing. I have 2 nitrogen, 28, over the total mass, which is 12 plus 16 for CO. Okay, 12 plus 16 plus 2 nitrogen, 28, plus 4 hydrogen, times it in 60. And then, 60. And then times it with 100, we try to get a percentage by mass. 28 over 60 times 100, you get 46.6% or 46.7%. See that, guys? 35 and 46%. Which one would you choose? And both are actually 50 kg per bag. So we actually can ignore the 50 kg. We just need to know, okay, both have 50 kg in mass. Which one having a higher percentage of nitrogen? Obviously, urea is the choice. Okay, so A answer is the urea by showing the working here. And for B, guys, what other factors will the farmer need to consider prior to making a final decision? Other than calculating the nitrogen content, we actually supposed to consider what? The first thing, be reality. In the reality, the first thing to consider is the price. Am I right? The cost. Which one is cheaper? We use that. Even though, let's say, for example, ammonium nitrate is actually 50% cheaper than urea. Now, even though urea giving you a slightly higher percentage between 35 and 46, about 10%, I would say so. All right. So, but the price is 50% cheaper. What would you choose? Obviously, I would take the ammonium nitrate from my point of view. So the price is one of the factors that we should consider. That's one. Second things I would suggest here is the acidity of both fertilizer. Now, why are they acidic? Because you have ammonium here and you have NH2 here. Now, both can act as a proton donor in water. So they are actually acidic. And in fact, by common knowledge, we know that fertilizer will increase the acidity of the soil. So sometimes when it's heavy fertilized, when the soil or the land is heavy fertilized, okay, heavy plantations, we add a lot of fertilizer for a long period of time. So what will happen? They have to remove everything. They have to put in some calcium oxide, lime powder, in order to neutralize all the acidity before they can start planting it new plants again. So they need a cooling period to actually avoid this higher acidity. When it's high acidity, that is no good for plantations, for the yield. And of course, it depends on what you are planting, right? So when the acidity is too high, that's no good. When the acidity is too low, that's no good. That's why we have to put in fertilizer to increase the acidity. So we have to control that. So two factors here I'm suggesting. One is the price or the cost. Another one is the acidity of the soil. All right. Number 3. Now, in a particular industrial processes in a gas phase, it is discovered that when either the temperature is increased or the volume of the reaction vessel is decreased, the yield of the product increases. Now, two factors here. Temperature increase, volume decreases. So we consider it one by one. What conclusions can you make about these particular reactions? From here, why temperature increase, the yield of the product increases? Means this reaction is an endothermic reaction. Am I right? Yeah, it's an endothermic. That's why when temperature increase, it will shift to endo, hence increases the product yield. So this is an endothermic reaction. That's one of the conclusions. And number 2, why the volume of the reaction vessel decrease, the yield increase? When volume decrease, pressure increase. Pressure increase will shift. Of course, this is a reversible reactions, by the way. When pressure increase, where does it shift? It shifts to the sites with less mole of gas. Am I right? Lower mole of gas, lower number of gas. So, and here they say the product increases, which means on the product side, you have less mole of gas. Less mole of gaseous product in these reactions. That's what we can deduce. Okay, so these are the two conclusions that we made. Number 4, a selection of the 12 principles of green chem is listed below. Now, these are the example. And for each of Haber and contact process, conduct a separate audit of the processes involved again each of these principles, which means like what I explained just now when I explained the whole 12 principles of green chem. So can you actually, based on these two processes and try to analyze it, make an audit that whether they fulfill all these principles? Does it fulfill all these, and which one it violated? Okay, which one it violates and which one it fulfilled in this process. All right, this is how we do an audit. So I'll leave it to you, and we will do discussions again in our tutorial sessions here. Number 5. Now, for each of the 3, sorry guys, it's not 3. I reduced 1, so it's 2. In each of the 2 processes considered in this section, the starting materials need to be purified prior to entering the reaction chamber. Like just now, when we do the methane gas, the natural gas, we need to desulfurizations, right? We need to remove the sulfur. And that's why we need to remove it. I explained just now why we need to purify the feedstock before they entering the reactions, before allow them to react, because we try to avoid poisoning of the catalyst if a catalyst is used. So to avoid impurities, okay, that can poison the catalyst, that's the first reason. Second, to avoid the formations of toxic byproduct, or to avoid the formations of byproduct. Because when you have impurities, when you allow them to react, you will definitely get more than what you need, because you have extra thing in the reactants. That's how we balance an equations, right? If we add 10% here on the reactant side, I will definitely get back the 10%, but just that whether the 10% is all in one product, which is the desired product, or they actually split 50% of the desired product, 50% is the byproduct. So 2 things we need to consider here. Why we need to purify, because number 1, trying to avoid the catalyst being poisoned by the impurities, and also to avoid the formations of byproduct. That's it for number 5. Okay, number 6. Now, in each of the 3 industrial processes, again, guys, it's not 3, but just 2. Identify in question 4, the one just now, which is Haber and contact process. The temperature of the reaction mixture increases in the converter. Now, what is a converter? A converter is actually the reaction chamber that converts your reactants into the product, in which this is the place where the reaction happen and produce the product. Okay, this is where the reaction takes place. And what causes the temperature to increase in the reaction chamber? So what does it mean? Now, from the contact and Haber process, when we consider these two reactions in industrial, we realize that in the reaction converter, in the converter itself, the temperature increases. And what causes this to increase? We are not increasing the temperature, guys. We are using the optimum temperature, which is 450 to 550. But in the converter itself, it realized that the temperature actually rise up to higher than 550, which is the maximum of the optimum. And why the temperature increases here? Because both reactions are in exothermic reactions, right? Contact and Haber both exothermic. So other than the temperature that we set, which is 450, for example, when the reaction takes place, and it is an exothermic reaction, heat energy will be released at the end of the reaction, and that's why the temperature increases higher than the preset temperature. Okay, that's the reason why. And what are the consequences of allowing this to happen? What happened when you allow this to happen, guys? If you look at B, now Haber process is an exothermic reactions. All right, you get ammonia, reversible, of course, contact process as well, and then you get exothermic. Now, if temperature is rising up in the converter, what will happen? Means temperature increase more than the optimum. So what happens when temperature increase? Where does the equilibrium shift? Backward. It shift backward. Why it shift backwards? Because it's endothermic on the left hand side. When it shift backward, what happened to the yield? The yield, percentage yield decreases. You will get less product when you allow this to happen. And what is done to address these consequences? And what they have done to avoid this? In the converter, we need coolant. Okay, we need a coolant. Just like our car engine, we have a coolant system to bring down the temperature of our engine, to maintain the temperatures of our engine combustions, right? Otherwise, it will overheat it, and what happened? The car will stop. You burn the engine. So we need a coolant in this case so that the temperature plus minus maintained at 450 to 550, not higher than that, even though it's an exothermic reactions. All right, so this is all like, it seems like you don't learn all these things, but yeah, why not? This is how we analyze the industrial process from the knowledge that we have. All right, how to reduce its coolant. And why is it getting less yield? Because it's an exothermic reactions at high temperature, it shifts to the left. This is the application part of our knowledge, guys. This is how we apply from chem, right? Okay, number 7. These questions refer to Haber process. Again, the same reactions. At 200 atm, that's the optimum pressure, the yield of ammonia doubles if the temperature is dropped from 500 to 400. So which means we reduce the temperature, it favor exo. Therefore, yield double. Makes sense, right? So why do the manufacturers continue to use a higher temperature instead? Why do they use 550? Some of them. Why not they use 400 or even lower? Why not? Because the same explanation, guys. If you use a low temperature, the equilibrium will definitely shift to the right to give you more yield. But consider the rate. What happens if you use a low temperature? The rate of reaction will be too slow. Make sense? So that is why they continue to use a, not to say high temperature, but they use a reasonable or compromised temperature in this case, rather than using a low temperature to maintain a reasonable rate. That's the answer for A. Alright, that's the answer for A. For B, guys, alternatively, if the temperature is kept the same, but the pressure inside the reaction chamber is triple. So instead of 200s, we increase it 3 times, so 600 atm. The yield actually doubles. So why do the manufacturer continue to use low pressure? Again, what is that reason? Because of safety reasons, because of cost, money, right? So we need to maintain high temperature or high pressure. In this case, we need more money. We need to build a stronger tank to withstand high pressure. All right, we need to burn more fossil fuels. We need to burn more energy to maintain high temperature. So we need more money. So this will increase the operational cost. That's the answer why for B. All right, number 8. Now, why will using a powdered catalyst rather than a large lump of catalyst in a reaction produce a faster chemical reactions? I guess this one everybody know how to do that. Powdered catalyst will give you a higher surface area and hence increase the rate of reactions compared to a large lump done with A. Clear? Now, for B, in both Haber process and the contact process, the catalyst is used in the form of pellets or hollow cylinder. Still remember I explained this when you have a cylinder and inside you have a lot of pores. The more pores you have, the higher the surface area. So they will use in terms of this. And why are powder not in use, guys? Why are powder not in use? The gas will go through these hollow things, all right? This whole thing is built by a catalyst. If it is a Haber process, then it's built by iron powder and make it into a solid bait, a solid cylinder with hollows inside. Okay? So, why powdered catalyst is not in use? We know that, we learned that. Powdered should be the catalyst used. But in industry, they are not using it. Why? Because when they are in a powdered form, which means they have high surface area. They are in a powdered form, right? But when they're in the small little particles, that would actually favor a deflagrations reactions. What is that, a deflagrations reactions? Deflagration is when under high pressure and high temperature, the particles of the reactants may be combusted. Because they're too small, the surface area is too high that it tends to be combusted. It burns, right? When it burns, these small particles will actually mix with the catalyst particles as well. And then there is a heat transfer or the heat wave from the small particles of the reactants towards the catalyst powder. Okay, and that transfer, it creates a huge hot air wave in that form. And that will continue the combustions of the particles, and that causes an explosion at the end. All right, so that's the reason why they try to avoid using powdered form reactants or powder form catalysts. No powder form, because under certain temperature and pressure, that will actually favor the deflagrations reactions and causes an explosion at the end. All right, so yeah, that's the answer. Number 9, I guess this is the last questions. What's the time now? Okay, 37 minutes. Okay, we are done. Okay, now the synthesis gas that is formed in the first stages of the Haber process is a mixture of carbon monoxide, carbon dioxide, and hydrogen. And this mixture can be used industrially to produce methanol. Now, look at A. Based on the two equations, one is to produce methanol, carbon monoxide plus hydrogen, and carbon dioxide plus hydrogen also produce methanol with water. Two different reactions here. And look at that. What conditions will you choose for the best yield from these two reactions? Explain your choice. Now, both are reversible, guys. All right, so what do you think? First, we talk about temperature, since they are both exothermic. So high temperature or low temperature should be used? Low temperature. I'm not saying that it is as low as room temperature. No, we try to get the optimum value. We can reduce the temperature in an experiment. We try to test, see which temperature can maintain a reasonable rate and also can maintain a reasonable yield. That is the best, or so-called the optimum temperature. So I would choose the lower temperature in that case, all right, because it favors the forward reactions. So that is in terms of temperature. What about pressure? So for these two, I have one gas on the right, I have two gas on the right. This one, I have three gas. So basically, on the right-hand side, they have lesser mole of gas. So I would prefer to use high pressure. Because high pressure favors the formations of the product with less mole of gas. And that will increase the yield. That's A. Okay, for B, what conditions would you choose? Oh, yeah, we are actually done, right? No, wait. Which condition would you choose for faster rate? So not about the yield, it's all about the rate of reactions. what condition would you choose? Of course, high pressure, high temperature. For B, both high. High temperature and high pressure. Because that will increase the rate of reactions without considering the yield yet. Alright, that's for B. And the industrial productions of methanol from the synthesis as a catalyzed reaction at low pressure and a temperature between 200 and 300. Explain the reason why these conditions are chosen. Why low pressure? Why low pressure, guys? Because, and why low pressure and as reasonably low temperature? Why is it low pressure and quite a low temperature compared to the what we deduce? Okay, now number one, they use low pressure in this case because to save energy, right? Because when we have a catalyzed reactions, we don't need high pressure. Like I said, in order to increase the rate, high pressure is part of it. But if it is a catalyzed reactions should have higher rate than uncatalyzed reaction. Am I right? That's the purpose of adding catalyst. So when we have added the catalyst, we don't need high pressure. So therefore, they use low pressure to save energy. And same goes to temperature between 200 and 300. We don't need high temperature in that case in terms of rate because we have a catalyst. So a same answer for both. In fact, just one answer for it. That's it. Okay, or if you want to give more than one because they said reasons, right? So you can say that why 200 and 300 in use? Because we say that low temperature shall give us higher yield from part A. So low temperature shall give us high yield, therefore we use 200 and 300 instead of even higher. Because we have a catalyst, can maintain the rate, now I can reduce the temperature to get higher yield. You see that? A catalyst will take care of the rate. A low temperature taking care of the equilibrium shift to give a higher yield. So one taking care of each, that we can get a balance of both. Alright, so last one for D, guys. Suggest what type of element might be involved in the catalyst that is used, and draw and label energy profile diagram to show how a catalyst affects the reactions. What type of elements usually involved in a catalyst use? We learned that in a homogeneous and heterogeneous catalyst. This is the reactions, exothermic, so I draw this diagram, lower energy for the product side. This is an exothermic reaction, and that's methanol. This is the reactant, right? So if it is a catalyzed reactions, how does it affect it? It reduces the activation energy. This is a catalyzed reactions, right? You just need to show this diagram. And what are the elements involved? Usually, commonly, all the catalysts used are transition element. Why they use transition elements? Multiple oxidation state. In fact, not two arrows, just one. That's the reason why you have multiple charges. You can change. You can catalyze a redox reactions. Okay, they can change from 2+ to 3+ for iron, right? They can change from plus to 2+ and 2+ back to plus for copper. See that? They can change the charge, meaning that they can catalyze the redox reactions. So that's the reason why. And that's it, guys, for this video. We're done with it. A little bit of theory and all the possible answer for all the questions. Of course, you may give different answer, and then we will discuss it again in the tutorial sessions. Thank you, guys. I will stop the video here.